In class, we watched an introductory video on chain rule where we learned how you would basically find a derivative of something by peeling off the layers, like peeling off the layers of an onion. So I'd like you to keep that visual in mind. And then I'd like to ask you the question, when do we use chain rule? Why would this rule even be necessary? Would I need to use it for a function like this one? Well, the answer to that is no, I don't, because for this one I would simply use product rule. So I don't need to use chain rule for something like that because I've got the product rule that find the derivative. So what about if I wanted to find the derivative of something like this? Would the chain rule be needed in this scenario? Again, the answer is no, because I have the quotient rule that would help me with that. So when is the chain rule necessary? What about if I had something like this? Instead of multiplying the cosine function by x squared, I plugged the x squared function into the cosine function. So do any of our existing rules tell us how to differentiate something like this? We know how to differentiate when I have a product of functions. We know how to differentiate when I have a quotient of functions. But what rule is in place when I have a composition of functions, where one function is completely plugged into another? Do we have an existing rule to tell us how to differentiate this? And the answer to that is no. So, because, the reason we don't is because this function that I've given you is a composition of two functions. That is the key right there. We don't yet have a rule to help us know how to take a derivative when I have a composition of two functions. That is when we need the chain rule. So to answer this question up here, when do we use chain rule? We use chain rule when we have a composition of two or more functions. So the chain rule is the following. When you're trying to take the derivative of a function of a function, a composition of functions, you would take the derivative of the outside function with respect to the inside function, and then you would multiply that by the derivative of the inside function. Now in the video we were calling this inside function a blop. So in this scenario the g of x would be our blop. And you take f prime of blop, whatever that is, and then you multiply by the derivative of the blop. So f prime of blop times derivative of blop. Let me give you a couple examples of what this would look like. So I'd like you to turn this paper over. And it's kind of like this. Let's say you wanted to find the derivative of f of x squared. Or f is just some other function, but it's a function of x squared. You would take f prime of x squared, and then you would multiply by, you would multiply by 2x. So it's like the 2x, or the x squared is your blop, and then you multiply by the derivative of that. Or let's say you had f of some trig function, like f of cosine of x. You would take the derivative of f, whatever f is, with respect to that inside function, and then you would multiply by the derivative of that inside function. And so on. That's how it works for all functions. Okay? So let's go ahead and do some examples of this. So in example 1, we have find dy dx for y equal to blop to the fourth. When I say blop, I'm referring to the 7 minus 5x to the fourth. So what I'd like you to do is just kind of recognize this as the thing that's being raised to the 4th power, so we call it the BLOP. And then recognize that your outside function, which we'll go ahead and call the outer layer, like of the onion. The outer layer of the onion is BLOP to the 4th. And then the BLOP is the 7 minus 5x. So what we're going to do is we're going to take the derivative of the BLOP to the 4th. And so we use the power rule for that because it's like something to a 4th power. So you would do 4 times the something, which in this scenario was the 7 minus 5x. And then that would be to the 3rd power, because when you're taking a derivative of like x to the 4th, the derivative of that becomes 4x to the 3rd. So this is 4 BLOP to the 3rd. And then we're going to go ahead and multiply by the derivative of the BLOP, which in this case would be 0, because the derivative of 7 is 0, minus 5, because the derivative of 5x is 5, so that's just negative 5. And then we'll just simplify that a little bit to make it negative 20, because I multiply the 4 and the 5, times 7 minus 5x to the 3rd power. And that would be our final answer. Okay, then we'll try a little bit harder of an example. The hard part, I think, is just recognizing what's on the outside and what's on the inside. So in this scenario, I guess you could say the BLOP will be the argument of the function. That's how you could think of it, the inside of the function. And then when I say the function, I'm referring to whatever the outer layer is. So in this case, the outer function is tangent of the BLOP. And then the BLOP is simply 2x minus x to the 3rd. So when you go to take the derivative of that, you want to take the derivative of the outside function first. This would be like your f of x. You take the derivative of f with respect to the BLOP. So you're going to do secant squared of BLOP, which is 2x minus x to the 3rd, times the derivative of the BLOP, which would, in this case would be 2, because the derivative of 2x is 2, minus 3x squared, because the derivative of x to the 3rd is 3x squared. And that's our final answer for that one. Now let's say you weren't sure if you did it right and you wanted to check your answer. Well, you can check your answers on the calculator by using the whole end derived thing. So let's take a second just to kind of remind ourselves how that would work. So you take your calculator out and you would plug the secant function into your y1. Or I'm sorry, not the secant function, what am I saying? The original function, which was tangent of 2x minus x to the 3rd. Then we're going to go ahead and take the derivative of that by hitting math 8 for end derive of y1, so I do the whole vars thing, comma x, comma x. Then I'm going to type in the answer that I got, which was secant squared. Well, I notice there's no secant button on here, but I remember that secant was 1 over cosine. So I'll do 1 over cosine of 2x minus x to the 3rd. And then that whole thing squared. So that's secant squared times 2 minus 3x squared. That's my answer. I want to see if my answer is right. So I'm going to graph these, but first I'm going to turn off the original function. I'm just going to unselect it, and then I'm going to go down to my answer and toggle over to the left by hitting the arrow, and then notice this is blinking. So I'm going to hit the enter button a bunch of times to toggle through my different choices, and it'll come upon an open circle. Then I want to graph these two functions, but before I do that, I'm going to go ahead and hit zoom and make sure that I'm on the trig window. So I'm going to hit 7 for trig, and then it's going to take a little while because it has to first compute all the derivative values to sketch them, and this is kind of a complicated function. So there's our derivative, and then we need to wait and see if our open circle traces along that graph. If it does, then our answer is right. And so there it is, tracing along the graph. So that tells me that I got the right answer, and it's just a way for you to check your answers if they aren't available to you. Okay, then moving along, getting even more complicated. So each example kind of gets a little bit more complicated than the last. Okay, so in this scenario, my outer layer is simply a power function. My outer layer is simply BLOP squared. So remember, f of x is your outer function, which in this case would be BLOP squared. And this BLOP is a big blob. This BLOP is a full-on quotient of two other functions. So what I have here is a quotient rule plugged inside a power function. So I'm going to have to use the chain rule, the power rule, and the quotient rule all in one problem. So let's go ahead and begin how we would start. So dy dx is going to be 2 times the BLOP, which is sine x all over 1 plus cosine x to the first power, because you reduce the power by 1, times the derivative of BLOP. So that's going to take some time because I need the quotient rule to be able to even figure out the derivative of this BLOP. So I'm going to go ahead and find my u and my v and all that stuff. So u in this scenario is sine x. V in this scenario is 1 plus cosine x. U prime would simply be cosine x because it's the derivative of sine, and then v prime would be 0 because the derivative of 1 is 0 plus negative sine of x because the derivative of cosine is negative sine of x. And then the quotient would be u prime v minus v prime u all over v squared. So u prime v would be cosine x times 1 plus cosine x. And then minus v prime u would be minus negative sine squared x, which becomes positive sine squared x, all over v squared, which would be 1 plus cosine x quantity squared. Well, as usual, I'm going to have to do some simplifying, as we usually end up having to do with trig derivatives. So then I distribute the cosine, and I've got cosine x plus cosine squared x plus sine squared x all over 1 plus cosine x quantity squared. Then I recognize again this identity right here. I've got cosine squared x plus sine squared x, which equals 1. So then this equals cosine x plus 1 all over the quantity of 1 plus cosine x squared. And then cosine x plus 1 is the same thing as 1 plus cosine x. So I can cancel out that factor and be left with 1 over 1 plus cosine x. So after that headache of quotient rule, this right here would be the derivative of the BLOP, the derivative of that inside function. So I multiply that derivative to the outer layer. So this was like the f prime of g, and now I'm going to multiply that by g prime of x. So that's 1 over 1 plus cosine x. And since this was to the first power, I can just go ahead and multiply straight across, so my final answer will be 2 sine x in the numerator all over 1 plus cosine x quantity squared. That is my final answer to this example. And as you can see, quite a challenging one at that. So what I would like you guys to do at this point is I'd like you to try this example 4. And I'd like you to stop the video here, try it out, and then check your answers to see if you get it correct. Okay, so what I would consider an okay answer, meaning it's correct but not all the way simplified, would be this: cosecant x all over cosecant x plus cotangent x. If you got that far, you did okay. If you went further and simplified further, the preferred answer would be 1 over 1 plus cosine x. So if you have questions on either of these, tutorial will be a good time to come in and figure out how to do them. To end the video today, we'll end with the most complex examples, which would be the repeated use of the chain rule. Because you're not always only going to have 2 layers, sometimes you might have 3, 4, or even more layers. Meaning you'll have one function plugged into another function, plugged into another function, plugged into another function. And then this function here is an example of that. This actually has 3 layers to it. And so we need to keep track of which one's the most outside, like the outermost function, the middle function, and then the innermost function. So let's keep track of all that. So it looks like the outer one is a power function because everything is being squared. So the outer function is blop squared. But then you have a function in the middle. You've got 1 plus cosine of blop. And what makes something a blop is if it's a function of x. So if you have something other than just x on the inside, that's a blop. And this is a little blop, it's just 2x, but it's not, because it is a function of x, it's not just x by itself, it's 2x, that qualifies it to be a blop. So then that blop is 2x. And we're just going to peel layer by layer, and we start with the outermost one, and then we do the middle one, and then we do the very inside one. So you always work your way from the outside and then work your way in. So you start on the outside, you work your way in. So we'll start with the power function. So let's go dy dx. So the power function is 2 times the blop to the power of 1. So it's 2 times 1 plus cosine of 2x to the first power. Then I multiply by the derivative of the middle. So the derivative of 1 is 0. The derivative of cosine is negative sine of that blop, which was 2x. Then, last but not least, I multiply by the derivative of the inside one, which is just 2. And then we're going to need to simplify a little bit because it's a trig function. So the first thing I can do is put all my coefficients together, the 2, the negative 1, and the 2, and bring that in front. So that would give me a negative 4 times 1 plus cosine of 2x times sine of 2x. Then we can do some distributing, and I'll go ahead and distribute the 4 and the sine 2x like at the same time just to save some room. So I have negative 4 sine 2x minus 4 cosine 2x sine 2x. That would be an okay answer. So this answer right here would be okay. But there is actually a hidden trig identity in this answer. And the hidden trig identity is right here. It's written a little bit backwards. In fact, maybe I'll move this to the open space that I have up here. If you recall, the double angle trig identity for sine says that if you have sine of a double angle, that is equivalent to 2 times sine of half that angle times cosine of half that angle. So in this scenario, my theta is equal to 2x because I do have cosine of an angle times sine of an angle. So my theta is equal to 2x. So if I wanted to package this back up into a sine double angle identity, I'd have to double this angle. I'd have to double the 2x and make it a 4x. But another interesting thing about the sine double angle is that the coefficient of the double angle is half the coefficient of the single angle. So in this case, my single angle coefficient is 4. So my double angle coefficient would be half of that, would be 2. So this whole part, the 4 cosine x sine 2x, could be rewritten as 2 sine 4x, which is considered simpler since it's not so much stuff going on. So then my final answer, or the preferred answer, is negative 4 sine 2x, that part didn't change, minus 2 sine 4x. And you're done. So you might be wondering, well, which version is she going to want on a test or quiz? I'm okay with the okay version. But here's the thing. Some of my test questions are multiple choice. The answer choices that would be given to you on a multiple choice answer would be the preferred versions. So you just have to be able to recognize when your answer would match the answer choices that are given to you. So if it's a free response question, I'm okay with this version. But if it's a multiple choice question, this is how the answer would be presented to you as one of the choices. All right, last but not least, we have another scenario where there are 3 layers. We have 3 different functions here. The first layer, or I shouldn't say the first necessarily, but the outer layer is the square root of all the junk on the inside. Okay? And you can also think of that as like BLOP to the 1/2 power. So 1/2 power means the same thing as a square root. And then the middle layer is the tangent of the BLOP. So you have a tangent function, and it's not tangent of x, notice, it's tangent of BLOP. So anytime you have something that is a function of x, if it's not x by itself, if it's a function of x, for example 5x squared, that is enough to constitute it a BLOP. That is why we consider this a 3-layer. Because it's not the square root of tangent of x, it's the square root of the tangent of 5x squared. There are 3 distinct functions here. The square root function, the tangent function, and then the 5x squared function. So we're going to work our way from the outside in. So the derivative of y with respect to x, we start with the power rule. So you do 1/2 times the stuff on the inside, tangent of 5x squared, and then we subtract 1 from the power. So 1/2 minus 1 is negative 1/2. Alright, so that was the outer layer. Then we go to the inside layer. We have to take the derivative of tangent, which is secant squared, of the BLOP, which was 5x squared. Okay, then we're down to the last layer. We just have to take the derivative of the BLOP. So we bring the 2 in front. So 2 times 5 is 10. So we have 10x to the first power. And that's the answer right there. But again, there's some simplifying that we have to do here, because this is definitely not anywhere near simplest. One thing I noticed are my coefficients are 1/2 and 10. And that'll basically just reduce down to 5, because 2 can go into 10 5 times. So then I see that in the numerator I'm going to have 5x and secant squared 5x squared. And all of that is going to be divided by the square root of tangent of 5x squared. So that right there is a very complicated answer. The kind of answer that you would probably want to check on your calculator. So if you take your calculator back out, and we're going to enter in, we'll clear out what we had before, but leave this part here because it's already set up to take the derivative of whatever you plug into y1. So I'll go ahead and plug in our original function, which was the square root of tangent of 5x squared. And then y2 is already set to take the derivative of that. And then in y3, we'll go ahead and plug in our answer, but we need to be careful. So I'm going to start with a parenthesis because I need to keep the things in the numerator together. So I had 5x times secant squared. So again, there's no secant button, but we do have the cosine button. So I'll do 1 over cosine of 5x squared. And then I'm going to square the cosine, just the cosine part, or the 1 over cosine part. So maybe to make that extra clear, we're squaring just the cosine part. So I have the parenthesis for the numerator, the parenthesis for the 1 over cosine. So this first parenthesis closes in the argument for cosine, which is 5x squared. the second parenthesis closes in just the 1 over cosine part, and then I need one last parenthesis to close in the numerator. And then I'll divide that by the square root of tangent of 5x squared. And I don't need any extra parentheses there, other than just to close the argument of tangent, which is 5x squared, and then to close the argument of the square root. Then I'm going to deselect the y1 so it doesn't graph that because that's too confusing. And I'll toggle back over here to turn it into the open circle. And then for this one, let's just go ahead. I think it's already set to zoom trig, but in case it's not, we'll hit zoom 7. And we'll patiently wait as it graphs the derivative. Takes a little while. And then we're going to hope to see that our graph, or our answer, matches this graph by looking to see if the open circle traces over this graph. And there it is. So goody, goody, goody. We did it correctly, and I will see you all in class.